Okay, here we're going to take a look at telescopes in each band of the electromagnetic spectrum. So let's start with the telescope that most of you have probably heard of, the Hubble Space Telescope, or the HST. This is a picture of what it looks like to the right. It's a reflecting telescope, like Newton's design. These things here are solar panels so that it can get power from the sun. This is the opening of the telescope here, which can be closed. It collects light, reflects it off a mirror, records it with a CCD, just like we talked about in the previous video. It has a 2.4 meter diameter, right? So it's 2.4 meters across here, which is a very large size telescope. And its function is to look at light in the near infrared to UV. So basically it covers the visible spectrum and then a little bit on each side. And it was launched in 1990 and it could run into the 2030s. It's still active and collecting data. And most of the really good pictures you've seen of planets are probably taken by the Hubble Space Telescope. It orbits the Earth at a distance of about 600 kilometers, and it goes around every 95 minutes. So that's how long its orbit takes, is 95 minutes to go around the whole globe. So you can imagine it's traveling through space really, really fast. So the Hubble Space Telescope, sort of the most famous telescope. It's in space, which allows it to collect visible light, UV and infrared, without any distortion from the atmosphere. I mentioned before that visible light penetrates through the atmosphere, but that doesn't mean it's not affected by the atmosphere at all. Some light, visible light, is getting absorbed, even though most of it makes its way down to the ground. So putting this telescope in space just helps us get the most clean, crisp images possible in the visible part of the spectrum. Now, the replacement for the Hubble Space Telescope is a telescope that's been in works for a while. It's called the James Webb Space Telescope, or JWST. This is what it looks like. It's a much bigger telescope, 6.5 meters as compared to 2.4 meters. It's also slightly different in where its function is going to be. It's going to go a little bit more towards the infrared and not quite as far into the visible spectrum. So the pictures that it's taking, what it's looking to do, is slightly different than the Hubble Space Telescope. It's basically going to take the Hubble range in wavelengths and shift it a little bit towards the red end of the spectrum. So get a little bit more infrared light and give us a totally new view of the universe. The hope is that will launch next March, so March 30th, 2021, and its orbit will be very different than the Hubble Space Telescope. It's going to be at a special point. This is sort of an aside. You don't need to know this, but it's going to be at the L2 point, which is the Lagrange 2 points, a special orbital point, and there are very technical reasons from that. But it's going to be much farther away from the Earth than the Hubble was, 1.5 million kilometers from the Earth. I'll give you one reason why it's going to be where it is that because it's looking to measure more infrared light, and the Earth is actually emitting infrared light, being farther away from the Earth will help it not see the Earth's signal, not be affected by the noise from the Earth. All right. Now, there is a telescope that is focused on infrared and has been giving us a good view of the universe in infrared. It's called the Spitzer Space Telescope. That was launched in 2003, and it also orbits far from the Earth, but it actually is basically in the same orbit as the Earth of the Sun, but out ahead of us. So it's sort of leading the Earth in its trip around the sun. So the images that you see that are infrared, mostly infrared, are probably taken by the Spitzer Space Telescope. For microwave, so if we go beyond infrared, longer wavelengths, we get into microwave. The most advanced telescope for that is also in space. It's called the Planck telescope. And if you remember, one of the examples I looked at in the first video was to calculate the wavelength of empty space. And I found that it was in the microwave. Well, empty space gives us a microwave signal, and the Planck telescope's job was to map out the microwave signal from empty space. And so it created a map like this. Red to blue, it's sort of color coded. So red would be like a little bit warmer, and blue is a little bit cooler, I think, in this map. But it's fairly evenly centered around 2.7 Kelvin. But there are slight variations. There's sort of slight granulation in the signal that the Planck telescope was looking for. And there have been a series of these telescopes. The first one was called the Cosmic Background Explorer, or COBE, and then there was the Wilkinson Microscopy, Wilkinson Microwave Anisotropy Probe, the WMAP, and those preceded it. And the Planck's telescope has given us just a more fine-grained view of the empty space, the temperature in empty space, which has a lot to do with cosmology, the study of the origin and evolution of the universe. So we probably won't do too much with this, but we'll touch on it at the end of the semester. Now we get to the longest wavelengths, or the radio wavelengths. And I got to visit this telescope. 2 of these 3 pictures are mine. This is the Green Bank Observatory in West Virginia, Green Bank, West Virginia. This is a picture that I took when I visited there 2 years ago, I think. I took a short summer course there, and it was just a really beautiful location. And then this picture is mine, and this one I brought in off the internet because I was not allowed to bring my camera this close to the telescope. One thing you should know about radio telescopes is they're very, very sensitive, and we use radio transmissions all over the place, right? Our cell phones and even our cars, and really any technology we have is probably giving off a radio signal. And so this telescope is in the mountains of West Virginia in an area that is restricted radio signal. It's a radio-free zone. And in fact, when you're on the campus, you can use your phones, but there's a fence set up, and you can't go beyond that fence with your phones. So I was able to actually visit this telescope, and even they brought it into this position where the bowl is facing up, and I was able to get up to this top platform and stand on this platform. It's probably the most beautiful sight you'll ever see. You feel like you're on the top of the mountains, and you can see just endless scenery in 360 degrees. So if you ever want to take a vacation to somewhere really peaceful and tranquil, I would recommend going to the Green Bank Observatory and taking the tour there. The telescope itself is just magnificent. It's 100 meters. Now you might ask, well, why do you make it so big? Well, one thing is bigger is better when it comes to the size of telescopes. And because radio waves themselves are so big, radio telescopes need to be extra big. So the size of the wavelength does affect the size of the telescope you need. To get long wavelengths like radio waves, you need a very big telescope. And the Green Bank Observatory is 100 meters across. So basically it's a football field across. And that football field is collecting radio waves and focusing them on a platform up here. and that was the platform I got to stand on. But up there's a detector that records the radio waves. One neat thing about radio waves is it doesn't need to be night, and it doesn't need to even be clear skies for them to operate. So the telescope right here could totally be taking data right now. Even though it's all cloudy and the skies are not clear, this telescope could be taking data because radio waves penetrate through atmosphere very, very well. And so as long as the sun's not directly in the way, it can look up and see the sky. The sky is not dark to the radio waves during the day. So this is a good moment to actually tell you that the sky is blue because the atmosphere scatters the visible light, and it preferentially scatters the blue light. So the reason why we can't see the stars at night is because we're seeing all this scattered blue light from the sun. If the atmosphere didn't scatter visible light, that light would come directly into us. And so when we look in the direction at the sun, we'd see a really, really bright source. But aside from that, the sky would be dark. Even when it's, cloud-free, clear skies. But the atmosphere does scatter visible light, scatters blue light, makes the sky blue, and also makes the stars not visible to us during the day. But for radio waves, they don't get scattered by atmosphere. And so the sky is dark for a radio astronomer 24 hours a day. The only thing that limits it is where the Earth is pointed at that time. So the sky rotates over it. This telescope is actually totally steerable, and it's the largest fully steerable telescope in the world, meaning that this telescope can be tipped up and down, so you can tell from this picture to this picture that it can tip up and down, and it also can rotate side to side on sort of a vertical axis. So this is one radio telescope. I wanted to show you another one because it's a different design. This is a similar idea to even the Hubble, where it's a reflecting telescope. The light reflects off and is collected up here. So the Hubble, the James Webb, the Spitzer, those are all similar designs. The next one is a little bit different in that it takes a telescope like the previous ones and it links them all together. So this is called the Very Large Array, and it's doing radio astronomy, and all of these telescopes are working in sync. So they're all pointed at the same point in the sky at all times. So it's not like they're each doing a different thing. They're all looking at the same object, and they're interconnected. So basically they're collecting data and adding all the data together through a process called interferometry. This is located in New Mexico, and interferometry is a way to expand the size of your telescope without making the telescope unwieldy. So the Green Bank is one 100-meter telescope. This is, many, many smaller telescopes that are linked together to work as one bigger one. And that's another way to do radio astronomy is through interferometry. All right, a few more. But now we're going to go to the smaller side. How do we look at the small wavelength light? Well, there's the Chandra X-ray Observatory for looking at X-rays. And because X-rays don't make it through our atmosphere, that has to go into space. So it's another space telescope. It was launched in 1999. It's orbiting around the Earth pretty fast, every 64 hours. And it gives us an X-ray view of the universe, which will be important for us when we look at things like black holes and neutron stars and pulsars and high-energy things produce X-rays. And most of the images come from the Chandra X-ray Observatory. Ground-based telescopes can't really observe X-rays. So there's not a lot of options when it comes to X-ray astronomy. For gamma-ray astronomy, as an undergrad, I got a chance to work on a gamma-ray telescope called Milagro. And even though gamma rays are even higher energy than X-rays, meaning that they're even less likely to pass through our atmosphere, the shorter the wavelength, the more it gets absorbed in our atmosphere. This is actually based on the ground. And I want to show it to you because A, I got to work on this telescope, and B, it's another alternative design. Because this is a strange telescope. It's not really what you would think of when you picture a telescope. It's more what you would think of when you picture a swimming pool. And so this is the telescope here, and there's a tarp over a big pool of water. It is really a swimming pool, except instead of people swimming in it, there are lots and lots of photodetectors. And so this is a view underneath the tarp. There's all these photodetectors in the water. Now, the way that this works is the gamma rays don't make it through the atmosphere and land in the water, but the gamma rays hit molecules in the atmosphere and cause other particles to cascade down. And so this telescope looks for those particles that come off of the interaction with the gamma rays in the atmosphere. So it basically causes like a particle shower, is a way to think of it, that the gamma rays hit the atmosphere and cause a particle shower down on the telescope. My job was to dig trenches around the telescope to add these additional sensors to help calibrate the detector. And it was just a fantastic location. It's in the mountains of Los Alamos, New Mexico, and I worked there for 2 summers. I think I was there. It must have been 2001 and 2002. So right when it was getting started, and yeah, it was definitely 2001 and 2002, and it went for another few years after that and ended in 2008. We now have a much better way to view gamma rays because we have put a telescope into space, and that's called the Fermi telescope. It essentially replaced Milagro. It's been in orbit since 2008, giving us a view of the gamma rays. Similar to X-rays, it's only the most high energy things that are going to emit that type of light. All right, so what I hope you take from this is just some familiarity with the names of these telescopes and the idea that in order to look at the full electromagnetic spectrum, you need a specific kind of telescope to focus in on a specific band of the light. And that telescope can have very different designs, but the location sort of affects what you can do. The best thing we can do is put telescopes into space, but that's obviously expensive, and so we've looked for different ways to view the sky that are more cost effective. But at present, we have telescopes in space for every type of light that we would need to put a telescope in space for, which is to say pretty much everything except for radio waves. There are telescopes orbiting the Earth collecting data. And so at present we have a really comprehensive view on the universe, which is only going to get better when the James Webb Space Telescope launches, hopefully next year.